So it's a pleasure for me to introduce Evgeny Shinder from Sheffield. So he will talk about semi-orthogonal decompositions for singular varieties. Please.
Okay, thank you for the introduction. Thank you very much for the invitation. It's an honor to give a talk in this seminar. Good morning. It's morning in the UK. I'll speak about derived categories and singular varieties. So what's the plan? There'll be three parts. So the first, I'll just give some reminders about semiorthogonal decompositions, exceptional collections, and algebraic K-theory in the smooth case. Then we discuss Kawamata decompositions in the singular case, and I give series of examples for curves, surfaces, threefolds, and blow-ups. And then I explain abstractions to Kawamata decompositions coming from algebraic K-theory and geometric interpretations of these abstractions. So kind of the third part is the most developed part, as you will see. So most of this talk is based on my work with Kalk and Pavic, but also there's some reference to other work with Karmazin and Kuznetsov. And yeah, some of this work, such as the definition of Kawamata decomposition, is inspired by Kawamata's paper on threefolds. Okay, so that's the plan, and let's begin. Yeah, so first I speak about derived categories, semiorthogonal decompositions, exceptional collections, and K-theory in the smooth case. So let's start somewhere. So I'll start with exceptional objects in derived categories. X is a smooth projective variety over any field, and we consider the bounded derived category of complexes of coherent sheaves. So I'll try to motivate what's going on in that category. So this category consists of complexes, in particular it includes all sheaves, and the point is that homes in this category are X between sheaves. So if you shift one of the objects, then the resulting home is the X group. So that's a device which carries all the information about all the X groups there are between coherent sheaves. And so an example of this category is if you take a point, coherent sheaves are finite dimensional K vector spaces, all higher X groups are vanishing, and every object splits as a finite direct sum of shifts of K. So that's the simplest possible case for the derived category. And so this motivates the definition that an object in the derived category, so a complex of coherent sheaves, is exceptional if its X groups are like those of a one-dimensional vector space, namely X0 is K and there's no higher or lower X. Equivalently, we can say that F generates a subcategory equivalent to dBk. So some examples and non-examples of exceptional objects. So firstly, if you look at line bundle and you compute X from it to itself, then you see that L is exceptional if and only if O is exceptional by untwisting. So it is independent on the choice of the line bundle, and it's equivalent to higher cohomology of the structure sheaf vanishing. So basically either all your line bundle are exceptional or they're not. And a fun exercise is to prove that a curve of positive genus has no exceptional objects. So how will it go? You first check line bundles, there's none, then there's vector bundles, and then you should look at vector bundles plus torsion sheaves. So every object will be direct sum of shifts of vector bundles and torsion sheaves, and then you check that none of them is exceptional. Okay, so this is specific kind of objects which will be used to decompose derived category into pieces. So now I speak about these pieces. So these are called semiorthogonal decompositions of derived categories. So we say that dBx, the bounded derived category of coherent sheaf, decomposes into A and B if A and B are full subcategories of dBx, and the homes backwards vanish. So it means that for every object from B and every object from A, there's no home from B to A. And then finally, decomposition in this case means that dBx is the smallest triangulated subcategory containing A and B. So we may ask why semi-orthogonal, not fully orthogonal. In fact, connected varieties do not admit fully orthogonal decompositions. That's why we only require homes to vanish one way. And these then are quite common. So in principle, semi-orthogonal decompositions, they mirror contractions in a minimal model program. So here is one example, Orlov's blow-up formula. If you look at, so here is like a typical example of a semi-orthogonal decomposition coming from geometry. A connected smooth subvariety, and we do a blow-up of Z. Then there's this thing that the category of the bigger variety, the blow-up, is decomposed into pieces where the biggest piece is dbx, and the other pieces are all equivalent to db of the center. I didn't specify the functors. It's like pull back, push forward with a twist. It doesn't matter for us now. And the number of those new pieces is codimension of z minus 1. For example, if codimension was already 1, there was nothing to blow up. All right, so yeah, so this is how semi-orthogonal decompositions come from geometry. And similar formulas work for projective bundles or other fiber bundles. Another thing we would care about in semi-orthogonal decompositions is how we can swap the order. So I said that they are not totally orthogonal, but still there's a way of changing the order. And it goes through the Serre functor. So Serre functor is tensoring by omega, by canonical class with a shift by the dimension. And Serre duality, if you think of it categorically, what it tells is that if dbx decomposes into A and B, then if we want to put A on the right, what we have to put on the left is the Serre functor applied to B. And the reason for this is that if we start computing Homs in the second decomposition from A to Serre functor of B, by the definition of the Serre functor, we'll be ending up with the Homs from B to A, which are vanishing. And then a bit more shows that it's the full decomposition. Okay, so right, so this is semi-orthogonal decomposition, an example, and how to change the order with the Serre functor. Now I relate exceptional objects and semi-orthogonal decompositions. So these go under the name of full exceptional collections. So let's look at a bunch of objects in the derived category, and we say that they form a full exceptional collection if, again, some properties are satisfied. So first of all, each of these objects is exceptional. So this I defined before. It means that its X groups are just K in dimension 0. In other words, the subcategory it generates is dbk. And then we require that those subcategories generated by these objects decompose semi-orthogonally of dbx. So we write it like this, and explicitly it means that there's no Homs backwards as before, and every coherent sheaf, and more generally every complex on dbx, can be written as an iterated extension of those objects EI. So what's the classical example, which actually predates the subject? It was Bailenson's bachelor's thesis or something like this. Bailenson was very young when he did it. So dB of Pn is O01 up to On. What does it mean? It means that X computation shows that there's no Homs backwards, and also standard argument with a diagonal on Pn cross Pn shows that these objects generate all coherent sheaves and all complexes of coherent sheaves. Okay, just maybe to give a flavor for the subject, let me state two cool questions, probably very difficult. One is about necessary condition, the other about sufficient condition. So firstly, if we have a smooth projective variety with a full exceptional collection, is X rational? So the examples of varieties with full exceptional collections are projective space, quadrics, Grassmannians, homogeneous spaces, some quiver varieties, and they are all rational. And yeah, but it's not clear how to approach such a question. And conversely, we can ask for sufficient condition. If we have smooth projective moduli space of stable quiver representations, so these varieties are cellular. They have a Tate motif and only PP cohomology. and they have this flavor of having a full exceptional collection, but it's not known how to prove this. Any question?
Is the first question even open for surfaces?
For surfaces, there is partial progress. I think for surfaces it's doable if it's not done, because we have classification of surfaces, and I think either it's done or one could hope to do it. Mm-hmm. I'm not sure. I forgot. But yeah. Any more questions or comments here? All right, so I move on and I speak a little bit about. Is there a question?
I think you can continue.
Okay. Yeah. Right. So I'll speak a little bit about the Grothendieck group and K-theory in the smooth context. So first of all, one algebraic avatar of derived category or triangulated category is its Grothendieck group. So it's given by generators are isomorphism classes of objects, and relations come from triangles. The object in the middle of the triangle is declared to be the sum of the two objects to the left and to the right. So, okay, that's the definition. If you know what the triangulated category is, you know this as well. So how do we think of this K0? So if we plug in dBx and look at complexes modulo these triangles, then we get the same as K0 of algebraic vector bundles, because basically everything will be filtered by sheaves or bundles, and then the relations will be the same. So you construct maps both ways and they are isomorphisms. Secondly, if we have semi-orthogonal decomposition, it leads to direct sum decomposition of the K0 group. Again, it follows easily from the definition. There are maps both ways and they are inverses to each other. And in particular, if we have full exceptional collection, then K0 of X is just Z to the R, where R is the number of exceptional objects by the previous formula plus the fact that dBk has Z as K0. So we can think of this as an abstraction to having a full exceptional collection. So if you know that your K0 has torsion, for example, Enrique's surface, who has Z mod 2 as torsion, or if you know that your K0 is infinite dimensional, such as elliptic curve, you know that you have no full exceptional collection. So there's like abstraction, and we'll see similar abstractions later on coming from other K-theory groups. Okay, so what about higher K-theory? So it's the subject coming from topology introduced by Quillen in the 1970s. And basically, the only easy example of higher K-theory is K1 of a field, and K1 of a field is the group of units in that field. And generally K1 has this flavor of units, and then higher K-theory is quite complicated. So if you want to say something interesting even about, let's say, K3 of the field of complex numbers, that's already very complicated. And what's relevant for us is that triangulated categories, and more precisely DG triangulated categories, they have K-theory defined for them. And it's defined in such a way that the definition extends K-theory of algebraic varieties. So K-theory of the triangulated category of coherent sheaves is isomorphic to K-theory of the variety. So a bit later, I'll give some words about how this is defined. It doesn't really matter for us. We'll be just using one of those groups formally. Okay, so that's Grothendieck group and a little bit about K-theory. And I want to give like a big picture now. So there'll be some more technical matters quite soon, but here's a big picture. So yeah, I want to think about birational geometry, derived categories, and algebraic K-theory. And yeah, I want to make the case that there are links, like connections between those. So first, between birational geometry and derived categories, that's a very classical thing going back to the 90s and maybe to the 80s. So Bondar-Orlov, Kawamata, Bridgeland, and nowadays Ballard, Faber, Kontsarkov, and Halpern-Leistern are all either expressing derived categories in terms of birational geometry or conversely or conversely thinking of birational geometry as controlled by derived categories. So it's very tight connection. And one example is this Orlov's blow-up formula, but there's much more. Second, derived categories algebraic K-theory. So, as I was making the case, K-theory is an invariant of derived categories. But furthermore, K-theory itself is most naturally defined in terms of triangulated categories, as in Thomas and Chabot work. And finally, birational geometry algebraic K-theory, if we understand the subject broadly, then algebraic K-theory will include things like Chow groups, Chow motives, Hodge theory, and then it plays a role of an invariant in birational geometry, in particular, abstractions for rationality may be coming from algebraic K-theory. All right, so this was the picture in the smooth case, and now basically the talk is about singular varieties, which adds an extra layer of complications to all this. Are there any questions or comments now? Okay, so we begin the more technical part. So I explain what I mean by Kawamata decomposition, and then I give the series of examples in dimension 1, 2, 3, and then for blowups as well. So before we do this, I introduce a simple dictionary of singularities. We wouldn't need very much, but I explain what kind of adjectives we need. So hypersurface singularities are those given complete locally by a single equation. Then locally complete intersection singularities are locally complete locally given by a regular sequence of equations. And then Gorenstein means that canonical class is a line bundle. And we have easy implications. Hypersurface implies LCI, just because we have only one equation. LCI implies Gorenstein. This is basically an adjunction formula. If you are LCI in a smooth variety, adjunction formula tells you that what your canonical class is, and that it's a line bundle. Okay, so some examples of singularities. So AN singularities, they are hypersurface ones. You have lots of squares plus a power of a variable. In particular, for n equals 1, it is just lots of squares. Those are called nodes or ordinary double points. And lots of things I'll be saying will be especially interesting for nodes, the simplest kind of singularities. And more generally, for threefold, we have something called compound AN. I suppose the definition goes back to Miles Reed. And compound AN means that you have two squares plus something. And the something is a reduced singular curve. There's a slight clash with terminology where AN is compound A1. It doesn't matter for us very much, just at some point there will be a result for threefolds which holds for all compound AN singularities, and we should know that it includes all AN. And maybe an example of something which is not Gorenstein. So all those were Gorenstein because we're given by one equation. If you look at the quotient singularities, for example, surface quotient singularities with a cyclic group, then it's Gorenstein if and only if it's SL2 action. So in terms of the weights should sum up to 0 mod n. At some point, we'll have toric surfaces, and then I'll ask for them to have Gorenstein singularities, so it would mean this. Okay, so this is the basic dictionary. Basically, the most important singularity for us is the node sum of all squares is equal to 0, and you just can keep this one in mind. So I start explaining what's different for derived categories of singular varieties, and the first thing which is different is that there are 3 triangulated categories attached to X, not 1 as before, which was DBX, but 3. The first one is DBX, bounded derived category of coherent sheaves, so with the same definition as before. The next one is a version of this where we look at only at perfect complexes, which are by definition finite complexes of vector bundles, or maybe locally finite complexes of vector bundles, and it's a subcategory of DBX. And then there's quotient of one by the other, which is called Buchweiz-Orlov triangulated category of singularities, where we take Verdier localization of triangulated category and you get the quotient, and that's the third one. So note that if X is smooth, what happens? Then dbx is equal to dperf. This is because by Serre's theorem, every coherent sheaf will be resolved by a finite complex of vector bundles. And one can upgrade this to every complex of coherent sheaves can be resolved by a finite complex of vector bundles. And so db and dperf are the same, and singularity category is 0. And this explains the name of the singularity category, something which is non-zero if X is singular. So on top of having these three categories, here are some typical difficulties when X is singular. So firstly, the functors are not always defined where we want them to be defined. So for example, derived pullback and derived tensor product, they require resolutions by locally free sheaves, which are infinite, and so they don't preserve bounded complexes. They will preserve perfect objects, but not bounded complexes. And similarly, Serre functor, which is the tensor product with omega, is not well defined on dbx. It doesn't preserve dperf in general if omega is not a line bundle. If omega is a line bundle, so if X is Gordenstein, then it's okay. And the third thing is mutation is difficult. So not every semi-orthogonal decomposition is admissible. I didn't define this. Admissible means that I can change the order. And in the smooth case, we always could change the order by putting Serre functor in. In the singular case, it's more complicated. Sometimes we put admissible inside the definition then. Right, so this is what I want to say about derived categories of singularity. So there are three, and we need to be careful with the functors, where the functors are going, and also with the orders. Now I'll speak a little bit about K-theory of singular varieties, and I introduce the K-1 group, which I'll need to be working with. So as we have two triangulated categories, we also have two K-theories. One is called G-theory, and the other is called K-theory in the classical literature. So G-theory is K-theory of coherent sheaves, and K-theory is the K-theory of vector bundles. So I said I'll say something with construction, even though we don't need it. It's topology. So one starts with a category with additional structure. There are various versions due to Quillen, Waldhausen, and others. One constructs a spectrum or a space from this category, and Ki are defined as homotopy groups of that space. And because these are homotopy groups, they have certain types of functoriality, and we're only using that kind of functorialities. So informally, I kind of think of this Ki and Gi as homology and cohomology. So let's see why. So firstly, if X is smooth, then we have a map from K to G, and it's an isomorphism because for the same reason as before, that every coherent sheaf is resolved by finite sequence of vector bundles. And what about functoriality? So G theory, it's about coherent sheaves, it's covariant for proper morphisms. So we can think of this as homology. And K theory is contravariant for all morphisms, so we can think of this as cohomology. And so this first map is then like Poincare duality between homology and cohomology. And what are other features of the subject is that G theory is easier to compute because it has a simpler localization property. And K theory is more interesting because eventually we probably care more about vector bundles than about coherent sheaves. Yeah, and then in general, that's quite a technical subject, which goes back to the 80s and has been developed recently as well. But yeah, so we wouldn't need very much of those technicalities. Okay, so we have those K theory of coherent sheaves and K theory of vector bundles. Let's see what else we have. Using this Schlichting's K theory machinery for DG categories, we can rewrite those as K theory of dbx and K theory of perfect X. And this will be convenient for our purposes because this will also relate to K theory of the singularity category. And so I was talking about higher K theory, but in fact, what I need is like the negative K theory, the lower one. So the spectrum that produces K theory, one can take negative homotopy groups of it. And then we have the whole like Ki labeled by integers. But when X is smooth, Ki and Gi are the same, and because dbx is a derived category, its negative K groups will be 0. So this only shows up when X is singular. And what is known about this, so not very much. So the bounds are known. So those ki groups for negative I, they vanish from dimension on. So for example, if you have a curve, it's only k minus 1 and that's it. And if you have a surface, it's only k minus 1 and k minus 2 and that's it. And this was done by Weibel in characteristic 0 in the 80s, and then recent breakthrough in 2018 by Kertstrunk and Tamme in arbitrary characteristic. So now finally, yeah, I explain why I care about k minus 1 and what we do with k minus 1. So if one starts with K-theory of dBx and the perfect complexes, one can make a long exact sequence, which includes dBx, dper of x, and the singularity category of x, and then take the k groups in that sequence. And then the end of that K-theory sequence will be this. So k0 of x going to j0 of x, the first map is the one I defined before. Then it goes to k0 of the completion of the singularity category. And then it goes to k minus 1, and then it goes to 0. So what happens here? So we need to take the singularity category, which I explained before, and take a idempotent completion of it. It's very important. Usually it's not idempotent complete. And so then the sequence works like this. So basically, for us, k minus 1 will be a tool to control some of the other groups in this sequence. Are there any questions or comments here?
So this is that sequence comes from the quotient that DSG is equal to DB quotient by dperf, right?
Yes, that's right. And there's a, so that on top of this, if I didn't complete, I would get k0x, g0x, k0 of d singular x, and then 0.
Yes.
But with this completion business, the sequence works like this.
So
yeah,
this is
yeah, but
only with this completion that you have the vanishing under. Thank you.
So we'll see more of this complete and complete quite soon. So, but yeah, but basically it's coming from the long exact sequence associated to the Verdier quotient of the triangulated categories. All right. So yeah, so this is actually what I can say, that k minus 1 is 0 if and only if singularity categories are idempotent complete. So this is because right, without the completion, the quotient of G0 by K0 is just K0 of the singularity category itself. And so if K minus 1 is 0, the completion and the whole thing have the same K0, and then by Thomason, there's some kind of lemma of Thomason, which shows that then it's idempotent complete. So basically this is kind of the abstraction we're going to use. So that K minus 1 is abstraction to the singularity category being idempotent complete. And later on, I'll explain how this is used and also what's the geometric meaning of this. Now I'll define the main object we study is Kawamata semiorthogonal decomposition. So we look at the Gordon-Stein projective variety and we look at the semiorthogonal decomposition of dBx of the following form. So it has first component A and then component Ci's with the following properties, that A sits inside perfect complexes of X, and each Ci are derived categories of modules of a finite dimensional K algebra. So how do we think of this? So there are several ways to think of this definition. So one is we think of A taking care of the non-singular part of X and Ci each having to do with singularities. And we'll see examples later on what I mean by this, that Ci controls the singularities. But on the other hand, if we put A equals 0, which is allowed, we get a bunch of finite dimensional algebras which decompose dBx. And this is generalization of an exceptional collection where all Ri's are equal to K. And here are two examples. So the first is a silly example. If X is smooth, I can just take A to be the whole thing and no other components. So this is what I mean by non-singular part. And an interesting example is P112, which can be done in all kinds of ways. It's a singular quadric, for example, and it has two exceptional line bundles, O and O2. So O1 is not a line bundle. it's a sheaf, and then C is the complement to O and O2 will be equivalent to derived category of kx mod x squared. So we'll see later on a general theorem about why it's like this, but at the moment we should notice that this kx mod x squared corresponds to the nodal singularity of this cone over the conic. So P112 has a single nodal singularity, and we think of this kx mod x squared as telling us something about that singularity. But as I said, it can be done many ways. For example, Kuznetsov result about quadrics applies here to give exactly this. It's like a Clifford algebra of this quadric. Any questions or comments here? Okay, so I'll list some properties of Kawamata decompositions. So as before, we have A and we have those algebras Ri, finite dimensional non-commutative K algebras. So what are the properties? Firstly, all Ri are Gorenstein. So if you know what Gorenstein means in non-commutative case, it's this. Second, yeah, so maybe I'll be giving the properties and explaining why they are true. So basically, this goes through Serre-Functor. So Gorenstein for varieties and for algebras is equivalent to having Serre-Functor on dperf, and then we'll have a functor on Serre-Functor on dperf x because x is Gorenstein, and it will induce one on every one of those algebras. So each algebra will be Gorenstein. Secondly, so I said before that we have three types of singularity categories, but this definition is such that it decomposes all three of them. So it comes from dB, but also it induces one on dperf. So it says that if we intersect, if we look at perfect complexes in each part, they decompose dperf of x. So this statement is not automatic, even though it's not difficult. It has to do with intrinsic characterization of perfect complexes as homologically finite. And then taking quotient of one by the other, we decompose the singularity category. So A is gone because A is perfect. And then we take the quotient at each place and we get singularity categories of those little algebras. And furthermore, if X has isolated singularities, then we won't have a direct sum decomposition of the singularity category into those pieces. So this is because it's known by result of Auslander that in this case, singularity category is Calabi-Yau, and then there's a trick by Bridgeland that Calabi-Yau categories, if you have semi-orthogonal decomposition, it's fully orthogonal. Like Holmes will vanish both ways automatically by the symmetry. Yeah, so it is in this sense, Ri carry information about singularities. That singularity category is about those Ri's. So this was the definition and some properties, and now I explain 4 constructions. First construction is in dimension 1, and that's quite cool. So what's the result? So we look at a nodal three of P1s. So for example, we can take a union of 2 P1s or add more P1s, but it should be a tree as the graph. And then X has a Kawamata decomposition where we put structure sheaf in the first place and a certain quiver in the second place. So R gamma is a path algebra of a quiver. You start from the dual graph of X and you double all the edges and you put a relation on top of this. I'll give an example in a second, but it's basically almost the same graph as gamma plus some easy relation put on it. So note that when X is P1, so it's only one component in that tree, we get O and O1. That's generalizes P1 case. So why is the theorem true? It's like an explicit construction of a tilting object. It's a bit like similar to, so tilting object. So we have to produce some line bundles which generate, and then we write some, like sum of O1s or something like this, and then we get that the corresponding Holmes are only in dimension 0. So it will be a tilting object. Yeah, so later when we talk about abstractions to Kawamata decompositions, I'll explain why graph of gamma should be a tree. And here is a fun example. So the first interesting case, we look at a union of two P1s. It has one node. And here is this algebra R gamma. So as I said, we take the dual graph, which has two components and one edge, and we double the edge, put the arrows in the opposite direction, and put the relation AB equals to BA equals 0. And the claim is that dB of this X decomposes into O plus a copy of dB of this quiver. And we should remember this algebra R node because it will be showing up in various contexts. We defined it for curves now, but it will keep showing up for threefolds later on. Okay, so these are curves. Now I'll speak about surfaces and so what's the statement? The statement is we know that certain types of surfaces with certain types of toric surfaces admit Kawamata decompositions. And the claim is that it's if and only if the class group of the toric surface is torsion-free. And furthermore, if the class group of the toric surface is torsion-free, then we have the decomposition into dBRs, where this Ri depend on the type of singularity at the corresponding toric chart. So let's see. So the number of so the R, the number of this algebra, is equal to the number of toric charts, and each toric chart can be singular or non-singular. And if it's non-singular, we put a K for this algebra. If it's singular of type AN, this is the Gorenstein toric surface singularity. Then we put Kx mod X to the n plus 1. So for example, when we have P112, the thing I mentioned before, it has 1A1 singularity and 3 toric charts, which correspond to K, K, and Kx mod X squared. So how is this theory improved? It's, we need to look at the toric resolution and construct a nice exceptional collection on the resolution, which then descends to something on X. And the something will be this, a bunch of algebras. So I gave an example of P112, which has such a decomposition, and then you may wonder about this condition of class group being torsion-free. That's some condition on the lattice. And for example, if you look at P2 mod Z3, where Z with this Z3 acting with 3 different weights, it has 3 A2 singularities. Class group of X has Z3 in the torsion part, and so there's no Kawamata decompositions here. Later on, we'll see how this class group is becoming part of the same K-1 abstraction. Any questions or comments about toric surfaces? Okay, so I'll speak about threefolds, nodal threefolds. So here, there's no general theory in the toric case. And basically what we have is 2 examples. And kind of both of them are due to Kawamata from the paper I was mentioning earlier. So the first is a nodal 3-dimensional quadric. Its Picard group is Z, class group is Z2. I'll explain later why I mentioned Picard group and class groups. It will be important. And there's a Kawamata decomposition with 3 line bundles. Namely, we can take O minus H, O minus 2H. They are line bundles and they are exceptional. And then we take a look at the complement, and either from Kuznetsov's work or Kawamata does it explicitly, we get the same algebra R node, which I was explaining in the case of curves. And another example is V6. So a nodal del Petrov threefold of degree 6. What is it? We can construct it by blowing up 2 points on P3 and contracting a line passing through them. It again creates one nodal Fano threefold. And we have Picard equals Z squared, class group equals Z cubed. And then Kawamata proves that there are 5 line bundles plus dB of the same algebra R node. And that's a very clever computation using the resolution and mutating objects on the resolution. So yeah, as I said, there's no kind of general theory for this yet. And it's also not very clear why it's the same algebra R node appearing in dimensions 1 and 3. It has something to do with having a node and also with Knurrer periodicity, which explains how singularity categories of those categories should be the same. But also one link between dimension 1 and dimension 3 is the blow-up construction, which I explain now on the next slide. So this is the fourth way of producing Kawamata decompositions by blowing up. So this generalizes, in an easy way, Orlov's blow-up formula. So I'm looking at Gorenstein projective X and Z and an LCI is a variety in there. And then I do the blow-up of Z inside X. And then the claim is that if Z and X both have Kawamata decomposition, so does the blow-up. So the proof is, okay, so it's easy, that's why I'm explaining it. So Orlov's blow-up formula holds in the setting as well. For dBx, we have the copy of dBx and then copies of the center. And then we plug in Kawamata decompositions for both X and Z. We get some things in the wrong order, but then we can use admissibility, which is part of the definition, so that we can reorder things to get a Kawamata decomposition of dBx tilde. So basically it's Orlov's blow-up formula, but the point is that it's useful here because what we can do, for example, we can take P3, which is smooth, and take this union of P1, so a singular conic, and blow up. And we get a threefold, which is singular and has a single node. So if you make a local computation for the blow up, you see that blowing up a nodal curve in a threefold gives you a nodal threefold. And okay, so schematically we have this. So Bourbon for Z, so decomposition for Z, and Baileyson decomposition for P3 implies Kawamata decomposition for X tilde. Namely, we get the same algebra R node as before, plus a bunch of exceptional objects in this case. And it's kind of a link how dimension 1 is related to dimension 3 by blowups. It doesn't explain the full story because those examples on the previous pages, namely the quadric and V6, they are not blowups, but still it's some reasoning for why it's the same behavior in dimension 1 and 3. All right, so this is what I want to say about constructions of Kawamata decompositions. We have some infinite series and some examples in dimension 3. And now I'll be explaining abstractions coming from K-theory. And this will, at some point, becoming very close to constructions we can make, and at some point it won't. So you'll see. So I'm going to use a little bit of K-theory and then its interpretation to show when there's no Kawamata decompositions. So here is a proposition, which is kind of the key, even though it's not very difficult. So if dBx has Kawamata decomposition, then k minus 1 of x is 0. So I explained all adjectives here. Let me explain the proof. So I mentioned that why we use k minus 1 is that it's non-zero if and only if, sorry, if it's 0 if and only if singularity category is idempotent complete. And then Kawamata decomposition tells us that singularity category of X decomposes into singularity categories of these algebras. And so what we do know is that each of these singularity categories of the algebras, they are idempotent complete. So then, because idempotent completeness is inherited by semi-orthogonal decomposition. So if each bit is idempotent complete, then the whole thing also is, and conversely, we see that the whole thing is idempotent complete as well. And so this tells us that k minus 1 is 0. So that was the result. It was not difficult. It was like just a collection of kind of various implications. And so, of course, we think of this as having non-zero k minus 1 is an abstraction to existence of a Kawamata decomposition. So in general, k minus I are poorly understood, but k minus 1 is understood better. And in particular, we understand it quite well in dimension 1, 2, and 3. And I'm explaining this now and what kind of abstractions it gives. Are there any questions or comments here? All right, so we move on. So now, again, I go through dimensions. So let's let me explain what is k-1 for curves. So this is very well understood. Let's assume, for example, X is a nodal curve. Then the claim is that k-1 is a free abelian group of rank equal to the Betti number of the dual graph of X. So in particular, if components are smooth rational curves, then the Betti number is just the H1 of the structure sheaf. So how is it proved? So so Weibel gave proof in the 80s, and we reproved it with the singularity categories in our recent work. It's not difficult. One just need to know like K0 and G0 for a curve. So here are the two key examples how it's supposed to work. So if you look at a tree has a Betti number equal to 0, and so k-1 is 0. And if you look at K1 of nodal cubic, everyone's favorite example, then there's a loop in the dual graph. So dual graph is defined such that every self-intersection gives you a loop, and it's a Z. So in general, we know k-1 for every curve, and it's always Z to the power n, and then it's given in terms of singularities and components and how things intersect. But for us, the consequence is that if a nodal projective curve has a chromatic decomposition, then all its components are smooth and the dual graph is a tree. So it looks quite close to Bourbon's construction. So Bourbon's construction was a tree of P1s. And here we know that components are smooth and graph is a tree, but there's a little gap between those. Namely, we don't know if you take nodal union of two elliptic curves, then we don't know. So probably it has none, but it's not proven this way because nodal union of two elliptic curves has still k-1 equal to 0. So some work may need to be done to completely match constructions and abstractions here. But in any case, lots of things are covered. For example, nodal cubic has none. All right, so these were curves. Now, surfaces. So for surfaces, k-1 recovers something we sort of know about. So if you look at normal rational projective surface with rational singularities, that's a natural context to work here with. And then it has a different flavor, k-1 a torsion group as opposed to free group. And it has other avatars such as Brouwer group or torsion in the class group. And in particular, such surfaces with torsion and class group have no chromatic position, which recovers the previous result about toric surfaces I mentioned. So how this is proved, I'll explain the proof for threefolds, and there'll be a similar but simpler proof for this one. Is there a question? Okay. Now I'd like to speak about threefolds, which is kind of the main interesting point. So every time I spoke about threefolds, I said Picard group and class group, and they were different, if you remember, at every time. And so Picard group, as you know, is a group of Cartier divisors, and class group is a group of Weil divisors. And when they coincide, X is called factorial. Right, so here is the formula. So X is a nodal threefold, k-1 is finally generated, and so then k-1 is finally generated, and we're saying what its rank is equal to. Namely, we need to take rank of Picard group plus the number of singular points minus rank of the class group. And they'll be explaining where is this coming from and how to think of this combination. But in any case, if X has a chromatic decomposition so that k-1 is 0, the rank is 0, so the rank of the class group will be equal to the rank of Picard group plus the number of singular points. And kind of, you see, in geometry, we may think of factorial as something good, but here we want the opposite of factorial. We want the class group to be as big as singularities allow for, namely the rank to be Picard rank plus the number of singular points. And we call such threefolds maximally non-factorial. So how does it work? So where are these things coming from? So if you remember, there was a sequence which has K0, G0, K0 of the completed singularity category and K minus 1. And working out this sequence in dimension 3, in particular comparing K0 and G0, so coherent sheaves and perfect complexes, we see that in this dimension with isolated singularities, compound and singularities, the difference between them is the same as between Picard group and class group. I was saying earlier that K0 is a bit like cohomology and G0 is a bit like homology, and the first bit of the filtration on those are Picard group and class group, which are themselves a bit like cohomology and homology. So in any case, what remains from this K0 and G0 is this injective map from Picard group to class group. And then we need to look at K0 of the idempotent completion of the singularity category. And then when we do idempotent completion, by Orlov's completion results for singularity categories, we just have to separate the singularities apart. And so it would mean that we take completion at each of the local rings and take their singularity categories. And then by the same reason I was explaining, so we need to take K0 of this singularity category, and then it will be the quotient of G0 by K0, and G0 will be about class group, which is this term here, and K0 will be Z in the local case. So in any case, what I'm saying is that the contribution of the K0 of the completed singularity category is this bunch of local class groups. And then the final term is K minus 1, which is what we had. So what I was doing, I was proving this lemma. And where we use compound and singularities is in this first place to show that it's only Picard group and class group which matter for G0 and K0. So in particular, it includes AN and nodal singularities. And that's the most interesting case. So we need to know what is the local class group of a node. And local class group of a node is Z, as the easy computation shows. So we get the sequence where we have for nodal ones. So I'm explaining now how lemma implies the proposition. In the nodal case, we have Picard, class group, and then Z to the number of singular points, because these are the local class groups. And then K minus 1 is the last term. So we sort of see the geometric meaning of K minus 1 is like, so this third term here in the sequence is the abstractions to Veil divisors to be Cartier, and K minus 1 measures whether all abstractions are realized or not. Okay, so this was some philosophy, but in any case, I hope I convince you that the lemma is provable and proposition follows just by taking ranks everywhere. And the lemma also implies my claim that maximal and non-factorial means they are maximal class group, because by the sequence, maximal possible class group will be Picard group plus the number of nodes. Okay, any questions or comments here?
So technically, how to compute K minus 1?
But you see, this is the sequence is the answer, right? So if you have if you give me a threefold, which is nodal, we just need to look at Picard group, class group, and the local class groups. And then you need to see whether you have enough divisors to separate your singularities. This is what it's a little bit unusual question, you know, like we usually want all Veil divisors to be Cartier, but here we want the opposite. We want as many Veil divisors so that they separate the singularity, so that you can find a Veil divisor which is not Cartier at one point, but Cartier at all other points. This means that K minus 1 is small. Yeah, so this sequence is the answer. Yeah?
Mm-hmm. So also in particular for singular variety to admit Kawamata decomposition, it's never factorial.
Exactly, yes. So it should be nodal one should be maximal non-factorial. This is why I was bringing up for this V6 and the quadric that Picard group and class group were different, and they differ by the number of singular points, which was a 1 there. But I'll do some more analysis. So let's look at Fano threefolds. This is maybe the most interesting case. So some classical terminology is this, that the difference between class group rank and Picard group rank is known as defect. And what we have explained is that Kawamata decomposition implies that defect is a number of singular points, and it is maximal possible defect in this setting. And we can think, okay, so what are the threefolds, maybe Fano threefolds, which are nodal, maybe Picard rank 1 for simplicity, and with maximal defect? And I know 3 of these, Q3, V5 which can have 1, 3, or 1, 2, or 3 nodes, hyperplane sections of Grassmann, like linear sections of Grassmannian to 5, and finally V22. V22 is a bit more complicated, so it's degree 22 index 1 Fano threefold. I don't know how many nodes it can have, and I think it's not known how many nodes it can have. And but it does have maximal defect. But the geometric construction is complicated. So on the other hand, I also know some Fano threefolds which are nodal whose defect is not maximal, namely all Fano hypersurfaces and all double covers, I'm not sure about complete intersections yet, are non-maximal defect except for the quadric. And the reason for this, there's a formula which counts defect in terms of certain hypersurfaces through the singular points, and then it's just by the formula, it's clear that it's never maximal. So just let me give you an idea what I'm talking about. So for example, let's look at a cubic threefold. And 10 is the maximal number of nodes on a cubic threefold. And there's only one of those up to isomorphisms called Segre cubic. And it's given by a very symmetric equation. You can compute everything about this. And in particular, so we know that Picard group is Z, and then class group, one can compute from a certain construction. Okay, let me give you the fun construction. So previously there was this V6 where we had to blow up 2 points on P3 and contract a line. Here we have to do something similar, but we just have to blow up maybe 5 points on P3 and then contract the lines passing through them. And there'll be 10 lines passing through them, which makes this link to X. And this will be the Segre cubic with 10 nodes. Okay, and this also, why I'm saying is that this is why class group is Z to the 6, because you take P3 and blow up 5 points and then make small contraction. So class group is still 6 because it doesn't change in the small contractions. And so delta Z effect is 6 minus 1 is 5. So it's not 10. So in particular, Segre cubic doesn't have such Kawamata decomposition, but furthermore, no hypersurfaces except for quadric can have 1. So I mentioned some difficult open questions and old ones, but they are new. These are new and solvable. So there are 2. So first, I think one needs to classify nodal Fano threefolds with Picard rank 1 and maximal defect. And I think the list shouldn't be very long. So we'll include the quadric, V5, V22, and maybe a couple of more, and hopefully not too much. So it needs to, for this one is to know numerology of nodal Fano threefolds. So Fano threefolds are smoothable nodal ones. So one needs to know, I don't know, so virus invariants, then links between those guys, then know how to compute defect, and maybe a little bit Hodge theory to compute the defect. But it's kind of elementary in some way. And even more interestingly, among those that have maximal defect, which ones admit Kawamata decompositions? So far we have only the quadric and V6, and it would be fun to have more, and this requires either, so the problem is that there's not really a technique here, so we need to either descend decomposition from the resolution or come up with a new technique of smoothing degeneration. It's not developed yet, such a technique. So work in progress with my former PhD student Pavic, we're doing V5, and even V5, there's some work to be done to answer this question. All right, so I'm wrapping up. Any comments about Fano threefolds? So so I'm just giving the summary now, what I was talking about. So the summary, singularities, derived categories, and K-1. So I was making the case that Kawamata decomposition is a natural generalization for exceptional collections to singular varieties, where dbk is replaced by dbr for a finite dimensional k algebra such as kx mod x squared. And those decompositions exist for curves, toric surfaces, and some threefolds. Then the abstraction we use is that if x is a chromatic decomposition, k minus 1 is 0, and then k minus 1 is interpreted for curves in terms of the dual graph or h1, for surfaces in terms of the Brauer group, and for threefolds in terms of the class group, Picard group, and the defect of the threefold. So in particular for nodal curve surfaces and threefolds, we understand k minus 1 quite well, providing good abstraction to decompositions. And what is missing is new methods of constructions of those decompositions beyond the toric surfaces case where there's a general method. And I suppose further study of the toric case in dimension 3 and higher, or of nodal finite threefolds, will lead to better understanding of these themes. Okay, and so this is the end of the talk. And if you have some questions that you wouldn't want to ask in Zoom, you can send me an email and I'll reply. Okay, thank you.
Well, thank you very much for the very nice talk. Are there any questions?
May I ask a question? So, by the way, thank you very much. Very impressive talk. And so, isn't that so the drive category of perfect complex is more difficult at some point?
So I think about K-theory like this, that in K-theory, people generally think that K-theory is more difficult than G-theory, basically because if you have a closed subset, I think it's the same, right? So you know, like if you take Z inside X, you close the subset, and you look at DBX mod DBZ, this is easy, this is just DBU. But if you look at dperf X mod dperf Z, this is not, like the perfect complexes, they don't have this easy Verdier quotient behavior for closed subsets.
Mm-hmm. So if dB of coherent have such decomposition, then it's kind of parallel. But in general, it is more difficult. Do you mean that? So, yes, please.
So I'm not sure I understand the question. So what we do is we induce the one on dperf from dB, and we see that the natural way. If we start with the one on dperf, it's not clear whether it's coming from dB.
So if so k minus 1 is non-zero, then so of course such a complete decomposition doesn't exist, but do you expect still some kind of structure, so decomposition, something like that?
So yes, that's right. So for example, for hypersurfaces, let's say for nodal cubic, right? We would want, so they have some decompositions, right? So there's this Kuznetsov's component for hypersurfaces, and it's kind of works for nodal ones as well, but it's not a complete decomposition. So I think of it more like generalization of a full exceptional collection. And so something like if we have a variety with a full exceptional collection, which degenerates to a nodal variety, then probably that nodal variety should admit a chromatic decomposition with its algebras. And then if k minus 1 is not 0, so there's no simple decomposition, and I don't know what kind of thing there could be in general.
Okay, thank you very much. And I have one comment. So there was some question on the surface case in the nearly at the beginning. So if the so if there is a full exceptional collection, then is it rational or not? And I think this is open even for surface, but in some surfaces of some fake projected plane and so on, so that some cases are checked. So this is just saying that the phantom category is non-trivial, and but the proof use something of Kuznetsov theory and so on. So it's non-trivial. So even for surface, this question is open, I think.
Yes, thanks. Can I add on this point? So fake projective plane, so I know this because I was doing this. So they have always torsion inside K0, which means that they cannot have a full exceptional collection. But things like Godot surface or the ones which is, or Barlow, the ones which have no torsion and keys. So I guess what you're saying is that when all the simple abstractions are checked, we don't know what to do anymore, because if the Hodge structure, Hodge diamond is diagonal and there's no torsion anywhere, then we just don't have a way of showing that the given variety of general type has no full exceptional collection.
But still, so yeah, actually that's right. But so for given apparently full exceptional collection is not full, so this kind of thing is proved.
But I suppose we don't know whether for surface of general type, they don't admit full exceptional collections.
Yeah,
right?
it's quite unknown. Yeah.
Yeah. Okay. So it's a little bit subtle. Maybe I underestimated the difficulty when. Yeah. Thanks. When I was explaining this. So we do have classification of surfaces, but those which are interesting here are general type, for which we have no classification, and even for specific surfaces, we don't know whether they have collections or not. That's right.
Yeah, that's right.
Thank you.
Thank you.
So do you have examples of singular varieties with non-isolated singularities admitting Kawamata decomposition?
Yes. So if you take the one with isolated singularities and multiply it by P1, you get 2 copies of your original thing, and singularities will be along P1s. It's a bit artificial, but they don't have to be isolated. But just if they are not isolated, we don't know how to abstract them, but we can construct them simply by spreading out the previous singularities along a curve or higher dimensional thing.
And yeah, the next question is quite like a random question. So for non-projective varieties, we also, so D curve also might be strictly smaller than DB. Then is there a way to also to have a similar study of the geometry of such modules and manifolds involving K minus 1?
So K minus 1 has this interesting spirit. It's like a global abstraction. So if you remember, there was a thing that Veil divisors should be separating points. So as soon as we know that we have several number of nodes, K minus 1 is about global behavior of Veil divisors. So if your thing is very local, then complete local, then there is no K minus 1. And that's kind of one thing I can say. But the other thing I can say, okay, everything was projective because projective have finite homes. If it's not finite homes, just the whole theory becomes a little bit funny. So it's like, you can look at derived category of a fine space, but it's kind of a big thing. It's not contractible so it's typically we do projective varieties, and singular projectives are almost as good as smooth in some sense, but open smooth are a little bit weird in this I don't know, that's how I feel. Maybe other people have different.
Thank you very much. Are there more questions? So if there's no more question, let's thank Evgeny again. So the next AGEA seminar will take place in 2 weeks. So it will be GMT 1, so it will be 8, 9, or 10 o'clock, depending on where you are in East Asia. And thank you. So see you in 2 weeks.
Okay, thank you very much for the invitation to this
Thank you.
seminar.
Yeah, thanks again for the talk.